So after reading example 6, they tell us that the sales follow an exponential pattern of decline. That tells us that y is equal to CE to the KT, and we also know that K will be negative. Now they do give us some information about initial conditions. They tell us that they dropped from 10,000 units per month. So we do know that when T is equal to 0, when this model started, y was equal to 100,000. And they also tell us that it dropped to 80,000 units per month. And that was 4 months after this started. So we also know that when t is equal to 4, y is equal to 80,000. So now we can use the first initial condition when t is equal to 0. That's going to automatically tell us that our C value, which is our initial value, is 100,000. And then I'm going to use the second initial condition to solve for K. So we have 80,000 is equal to 100,000 to the K multiplied by 4. So I'm going to start off and divide both sides by 100,000. 80 divided by 100,000 gives us 0.8 equal to e to the 4k. I'll take natural log of both sides. And I do that because the e will cancel and just leave me with 4k. And then I will divide both sides by 4 to get that k is equal to 1/4 natural log of 0.8, which I will round that to 4 decimal places and get approximately negative 0.0558. So now that we have found K, we know that the entire model looks like this. There's our C value plugged in, and there's our K value plugged in. They want us to find the sales after another 2 months. Be careful with that word another. Another 2 months would mean 6 months in. So we want to evaluate the function at 6. So I'm plugging in 6 for T, and that's going to give me approximately 71,500 units. Our last example is going to use Newton's law of cooling, which is relevant to us because it states that the rate of change of the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So this has to do with, say for example, you take a cup of hot coffee and you set it into a room that is not as hot. Eventually the coffee is going to drop temperature. The rate of change of that temperature is proportional to the difference between the temperature of the coffee and the temperature in the room. So we start off and they tell us that y represents the temperature of an object in the room. The room is kept at 60 degrees. The object cools from 100 degrees to 90 degrees in 10 minutes. We want to know how much longer will it take it to decrease to 80 degrees. So first let's set up a differential equation using the fact that the rate of change, so I'm looking up here now, I'm using the fact that the rate of change of the temperature of an object, y is the temperature of the object. So its rate of change would be represented by dy dt. So there's the rate of change of the temperature of the object, is proportional to, so is equal sign proportional to, constant of proportionality k, the difference between the object's temperature, so the difference between the object's temperature, y minus, that's the object's temperature, y, and we're going to subtract the temperature of the surrounding medium. So the temperature of the surrounding medium is the 60-degree room that it is kept with. So now we have our differential equation. I'm going to go ahead and separate variables. So I'm going to get all the y's on the left side of the equation and the t's on the right side. So I'm going to divide both sides by y minus 60 to get it away from the right side of the equation. And I'm also going to multiply both sides by dt to get it off of the left side of the equation. Now that I have and I still have a dy on the left side. Now that I have my variables separated, I can go ahead and integrate both sides of this equation. On the right side, that's going to be a natural log absolute value of y minus 60. On the left side, we get natural log. On the right side, we're just going to get kt plus c. I will add, it's important to note that we do have an inequality in here. They told us that we're interested in when it decreases to 80 and it started at 100. So for this model, the temperature of this object is being kept between 80 and 100 degrees. We're only talking about the time from when it started at 100 degrees to I want to know what time does it end at 80 degrees. So we have this. Because we know that y is between 80 and 100, y minus 60 is definitely positive, so I don't need to use absolute values when I write y minus 60 on the inside of that natural log function. So I'm going to go ahead and redo this equation. I'm going to rewrite it by solving for y. So I'm going to use e on both sides of this equation. Equal out the natural log. So I'm left with just y minus 60 on the left side of the equation. On the right side of the equation, I'm going to use some rules of exponents to break up the sum that's in that exponent. I could write it as e to the kt multiplied by e to the c, because I know rules of exponents would tell me to add those exponents to get what we had before. And I did that because e to the c is just a constant, so I'm just going to call it c. I'm just going to put it as ce to the kt on that right side. So now I can finish solving for y and get that y is equal to ce to the kt plus 60. Now that we have an expression for y, let's use some of our initial conditions. We know that the object was initially 100 degrees, so we know that when t is equal to 0, y was equal to 100, and so I'm going to plug in 100 for y and 0 for t. Anything to the 0 power is 1, so I get that 100 is equal to c plus 60, which tells me that c is equal to 40. Now we need to go a step further and solve for the value of k, and in order to find k, we're going to use the second initial condition, that we know it's 90 degrees after 10 minutes. So we know that when t is equal to 10, y is equal to 90. So using that, I have the equation 90 is equal to 40, because that was our c value, e to the kt plus 60. I'm going to solve for k, so I'm going to subtract 60 from both sides. I'm then going to divide by 40 on both sides. I'm going to use natural log to cancel out the e. And I should have plugged in, I need to plug in 10 for t. See, I'm missing that. So I'm going to go back into all these t's and replace them with a 10. Because we're plugging in 10 for t and 90 for y. So at this point, we're ready to divide by 10 to see that k is equal to 1/10 natural log of 3/4, which is approximately 0.02877. So now we know that the model for our equation is y is equal to 40 e to the negative 0.02877 t plus 60. We are trying to figure out how much longer it will take for the object to decrease to 80 degrees Fahrenheit. So I want to know, what is t down in the equation? And I'm going to plug 80 in for y. And I'm going to solve for t. So I will subtract 60 from both sides. Then I will divide both sides by 40. Then I will take the natural log of both sides of this equation because I want to cancel out the e. Natural log on the right side will cancel the e and just leave me with what's in the exponent. And then I will divide both sides by that decimal. to conclude that T is approximately 24.09. If T is about 24.09, remember that already we had 10 minutes pass. 10 minutes had already gone by. So I need to take those 10 minutes away to conclude that it will take about 14.09 more minutes. That's what we were looking for. How many more minutes will it take to cool to 80 degrees?